All right, let's talk about something we all see in textbooks, the perfect circuit. But today, we're going to peel back that layer and get into the real world. We're going to figure out the hidden physics behind why our gadgets actually work the way they do. And it all starts with a couple of familiar puzzles. So let me ask you something. Have you ever been in your car at night, you go to start the engine, and for just a split second, the headlights dim? Or, maybe you felt a battery getting kind of warm after it's been running for a while? Well, guess what? Those aren't glitches. Nope, they're actually clues. Clues that point to something fundamental, something hidden inside every single power source out there. Okay, so to really get a grip on the real world, we kind of have to start with the fantasy world first, the ideal circuit. You know the one I'm talking about, right? The one from the textbooks where every single drop of energy from the battery makes it to the light bulb. It's this perfect, clean world of 100% efficiency. And in this perfect world, we've got two big ideas we need to keep straight. First up is something called electromotive force, or EMF for short. Think of this as the total energy the battery gives to each little bit of charge. It's the push. Then we have potential difference, or PD. This is the energy that gets used by something in the circuit, like a lamp turning it into light and heat. Now, in our perfect little textbook circuit, the energy supplied, well, it exactly matches the energy used, a perfect balance. So here are our main characters, right? You've got the cell, that's our energy source, and then you have the things that use that energy, like resistors and lamps. On paper, it looks so neat and tidy. But, well, you know what they say. Reality is always a little bit messier. So what is it? What's the thing that makes the real world so different from our perfect drawing? Well, it turns out there's a hidden culprit, something lurking inside every single power source that just messes the whole thing up. And here it is. The big secret is that inside every real battery, there's a tiny built-in resistor. And it's not something we put there on purpose. It's just part of the battery itself. The chemicals, the metals, they all put up a little bit of a fight against the charge trying to get through. We call this internal resistance, and we use a lowercase r for it. And this is the source of all those weird things we see in the real world. Just imagine those little electrons trying to fight their way out of the battery, pushing through all those chemicals. It takes work, and that work, that struggle, turns some of their electrical energy into heat. That's why your battery gets warm. Now, that energy being lost as heat, it has a direct effect we can measure. It creates a voltage drop, but here's the crazy part. It happens inside the battery before the electricity even gets out. We call these the lost volts. And because of them, the voltage you actually get to use at the terminals is always going to be less than what the battery's truly capable of producing. And this all boils down to one super important equation for any real-world circuit. The voltage you actually get to use, we'll call that V, is equal to the total energy the battery can supply, that's the EMF or E, minus those pesky lost volts. And those lost volts are just the current, I, multiplied by that internal resistance, little r. Okay, so this isn't just some tiny little correction we make to our math. No, this has massive consequences for how we design pretty much everything, and it leads to this big fundamental trade-off. Check out this graph. This is where things get really interesting. What you're seeing here is the amount of power a battery delivers as we change the resistance of whatever we plug into it. And look, the power isn't just a flat line. It goes up, hits a peak, and then falls back down. So the big question is, what's so special about that peak? Well, that peak happens at one very specific sweet spot. A battery delivers its absolute maximum punch, its maximum power, when the external resistance, the load, is a perfect match for the battery's own internal resistance. This is a huge deal in electronics. It's called the maximum power transfer theorem. But, and this is a huge but, there's a catch. When you're running at that maximum power point, how efficient do you think the battery is? It's only 50%. That means for every bit of energy you get out to use, another bit is being wasted as heat inside the battery itself. Half your power is literally being wasted. And this is the big trade-off I was talking about. You have a choice. Do you want maximum power? Then you match the resistances, but you have to live with a terrible 50% efficiency. Or do you want maximum efficiency? In that case, you make the external resistance way bigger than the internal one. You waste very little energy, but you also get a lot less power out of it. Power or efficiency. You can't have both at the same time. All right, that's enough theory for a minute. Let's make this real. We're going to take everything we just learned and apply it to an actual problem. So here's the situation. Imagine you've got a battery. You take out your voltmeter, and with nothing hooked up to it, you get a reading of 13.0 volts. Okay, then you connect a lamp. Suddenly, the voltage reading drops to 12.0 volts, and you see that the lamp is drawing 3.0 amps of current. So the question is, just from that information, can we figure out that hidden internal resistance? You bet we can. Let's walk through this. First step. That first reading, the 13.0 volts you got when nothing was connected, that's our true EMF, the battery's total potential. Step 2, we saw the voltage drop from 13 down to 12. So where did that 1.0 volt go? Bingo. Those are our lost volts. They got lost inside the battery. So for the final step, we know we lost 1.0 volts, and we know it happened because 3.0 amps were flowing. Well, Ohm's law tells us resistance is just voltage divided by current. So 1.0 volt divided by 3.0 amps, and we get an internal resistance of 0.33 ohms. See? Not so bad. So you might be thinking, why do we just spend all this time talking about a teeny tiny hidden resistor? Well, because understanding this little guy is absolutely 100% critical to engineering basically every electronic device you've ever used. So let's just recap the big takeaways here. 1. No power source is perfect. They all have internal resistance. 2. This resistance makes the usable voltage drop when you start pulling current, and that's why your car's headlights dim when you start the engine. That starter motor pulls a massive current. And 3, this whole thing creates that unavoidable trade-off between getting the most power versus being the most efficient. It's a choice engineers have to make constantly. And that leaves me with one last question for you. Think about your smartphone battery. When the engineers were designing it, what do you think they chose? Did they go for maximum power, so your apps run lightning fast but the battery dies quickly? Or did they go for maximum efficiency, to give you the longest possible life between charges? Now you understand the physics behind that choice they had to make. It all comes down to that tiny, hidden resistance. Thanks for diving into this with me.